Okay, let's start from here. I think I just want to uh, remind you some aspects of the periodic table. You know already the categorization of the elements that we considered under geochemical classification, right? So the geochemical classification, under that we classified elements into different groups, right? So one of such groups is the rare earth elements, right? You remember this is the rare earth elements, and from lanthanide to lutetium. Okay, it starts from lanthanide to lutetium. So basically, this is the set of elements which should lie on the periodic table, right? So from 57 to 71 atomic number. And then we have another group, actinide series, but this one we do not consider much in geology. Okay, but the rare earth elements are very important because these are the elements that we consider in a lot of magmatic processes. In addition to these REs, we in igneous processes we consider the high field strength elements that are grouped here. Okay, zirconium, niobium, hafnium, and tantalum. Right. So these four is considered as basically high field strength elements. Of course, as we learned, there are other high field strength elements also, but frequently used high field strength elements are these ones because they show very specific characteristics which are identified to recognize different igneous processes. Okay, magma mixing or tectonic setting even. For example, for the rocks, for the igneous rocks formed at subduction zones, or the subducting slabs release lot of fluid and melt due to friction. Okay, so these melts come as uh, magma and erupt in oceans, and finally they will configure into island arcs, right? For example, the Japanese islands, the whole island set, the entire island series is made up of this type of island arcs because the rocks there formed at a subduction zone. So this downgoing slab produces a lot of melts, and that melts finally crystallized as arc lavas, arc magmas, or arc lavas. They come up and crystallize. So all the Japanese islands is made up of more than 80% of uh, arc type rocks, right? So in these arc type rocks, it's characteristic that this zirconium, niobium, and hafnium, tantalum, these set normally we consider as couples: zirconium, niobium, and zirconium, hafnium, and niobium, tantalum. These two, each of two is considered as couples. They show similar depletions in arc magmas, right? Which is different from mid-ocean ridge basalts. More magmas, you don't see that feature, right? So this type of variations we are very useful in identifying the original tectonic setting. So trace element. So out of the trace elements, rare earth elements and these high field strength elements are very important. Okay, so you can see this rare earth element sequence increasing atomic number from left to right, and remember from left to right, the incompatibility also changes. Okay, you remember the incompatibility? We define the incompatibility how an element incorporates into the melt, right? If it has a preference to melt, then we call that element is highly incompatible. But if that element is more prefer they like much the solid phases, then we call it compatible, right? So I am telling now here, the incompatibility or the degree of incompatibility decreases. Sorry, the degree of incompatibility decreases from left to right. From left to right, the incompatibility decreases. Okay, so highly incompatible elements you have here. Uh, Highly incompatible, I'll put it as HI, highly incompatible elements towards the left hand side. Okay, so that means if you want to say lutetium, it is not very incompatible. Okay, always remember, rare earth elements are anyway incompatible. They can be accommodated into melt because there is preference anyway, but relative incompatibility is very high at this left hand side. Okay, from left to right, the relative incompatibility decreases. So therefore you have the highest incompatibility in lanthanum, whereas you may have the least incompatibility in lutetium. Okay, the same thing is true. If you take the compatibility, the opposite will be true, right? So from right to left, the compatibility decreases from right to left. That means you will have very high compatible elements in your right hand side. So your right hand side will be highly compatible, whereas your left hand side will be uh, highly incompatible, right? So this is highly incompatible and this is highly compatible. Okay, so incompatibility decreases in this way, incompatibility decreases in this way, and compatibility decreases in this way. Okay, so this is actually a relative change or relative difference. So you don't think that although you have the highest compatible element in your right hand side, you don't think that lutetium, being the highest compatible element, will not be partitioned into any melt. No, nothing like that. Lutetium will go there, right? Lutetium will partition into a melt, although it is the highest compatible element, but relatively its partitioning behavior to a compatible phase will be less in comparison to the left hand side element like lanthanum. Okay, so anyway, the lanthanum will have a high preference compared to lutetium when you consider a melt. But in the case of compatibility, lutetium will be having a highest compatibility preference if you compare it with other rare earth elements in this group. So, but it doesn't mean that lanthanum cannot go into a solid, right? Lanthanum also goes into the solid. It doesn't mean that it doesn't go, but relatively it has a less preference and a less what do you call the compatibility. Okay, so this is a relative type of compatibility and incompatibility issue here. So in any melt, you might find all these rare earth elements, but the degree of their partitioning will be different. So you will have basic this type of relative difference. So this means, in other words, if you take the partition coefficients, the value of the partition coefficients, if you consider the partition coefficient between rare earth element, between a given rare earth elements and a melt, okay, whatever the melt, maybe basaltic or granitic or whatever, if you consider their partition coefficient, always this lanthanum, cerium, like this left hand elements will have high partition coefficients because they have the preference to go into the melt. Okay, here, so this side you will have high partition coefficients compared to that of this side. Okay, because the right hand side has less incompatibility. It doesn't mean that the partition coefficient is zero or something. No, right? It will have some value, but low value. In the case of compatible elements, if you are considering the partitioning of a given rare earth element into a solid phase like cyanopyroxene, for example, when the pyroxene is crystallized, uh, the 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 compatibility, the highest compatible elements will go into uh, the solid phase, right? But it doesn't mean that these elements, these yeah, these rare earth elements will not go, right? They will also go, but these ones have higher preference. That means you will have high partition coefficients between solid and rare earth elements for these compatible elements. Okay, always compatible elements have high partition coefficients uh, uh, between the solids and their uh, relative rare earth elements, right? If you take a liquid phase, then you will have high partition coefficients for incompatible side elements, right? Always remember this partition coefficient is defined, as we said before, between a solid or a liquid phase, right? Partition coefficient is given for an given element between between a solid or liquid phase, right? When this element is partitioning into a liquid phase, that means more incompatible elements will have higher partition coefficients. The opposite is there for the compatible elements when you consider solids. Okay, so this is an important aspect that you have to always remember, because in different situations you cannot think twice. You cannot think twice, because you need to know, okay, this is compatible, then it should have a preference to the solid. That means its partition coefficient should be high if you are considering the solid element partitioning behavior. For if you have a liquid there, then incompatible elements will be having a high preference to be partitioned there. That means your partition coefficient should be high if you consider liquid element partition coefficient. Okay, so that is always you have to keep in mind. Okay. Right. So let's see the same thing that we just started talking on, the similarities in the D values, right? Similarities and contrasts, the differences and the similar features of D values. D values means these partition coefficients we are talking about. Okay. So you have the partition coefficients. Always remember this partition coefficient is defined with the concentration in the solid divided by concentration in the liquid. So the difference. So for the compatibles, you always have preference to the solid. That means for if you are considering the compatible elements, then their partition coefficient will be always high in terms of the considering whatever the phase that you are considering, the solid phase. So as I said before, uh, the incompatibility decreases towards the right hand side, and compatibility uh, decreases towards left hand side, right? In other words, you can consider again this as the compatibility increases towards the right hand side, the same thing, right? We said incompatibility decreases to the right hand side, that means compatibility increases. Okay, right? The same thing you can say in different ways. Okay, the different ways, that means as I said, these right side elements will have the highest compatibility. Okay, because their compatibility increases. So normally we divide these trace elements into subgroups. Into subgroups means we can divide from here, something like this. Okay, so from here to left, and then you can again divide usually from somewhere here. Okay, but sometimes it might go to somewhere like dy, but just keep like this, right? And again Sometimes this boundary comes to the samarium also, but for the time being, we'll take it neodymium. Okay, right? It doesn't matter. Even you can take somewhere here also. Anyway, so to the left hand side we call light rare earth elements. Okay, left hand side we call light rare earth elements because I said it because these two have very similar features. So therefore, it doesn't matter where you put the boundary. Okay, right? Preferably we'll put it here. Okay, we'll put it here. Right. To the left-hand side, you call it light rare earth elements, and this extreme right-hand side here, you can call heavy rare earth elements. Okay, heavy rare earth elements, or you can write it as HREE, HREE, heavy rare earth elements. To the light rare earth elements, you can write it as LREE, light rare earth elements. So the between to these two groups, you have the middle rare earth elements, right? MREE, middle rare earth elements, right? So this classification is also useful because sometimes we use these terms as light rare earth elements, heavy rare earth elements, like that. Okay, right. So when you go here, you can see this statement. What is it? Says heavy earth elements are less incompatible. Is that correct? Heavy earth elements are less incompatible, right? I think you can remember I told you the incompatibility decreases to the right hand side, or in other words, compatibility increases. So that means heavy earth element should be less incompatible. Okay, so they prefer solid phases. That means, right? Incompatibility decreases means their compatibility increases. Okay, so their preference little by little goes to the solid phases rather than a liquid. So when you have two phases in a system, right? So suppose you have a magmatic system, you have the magma, and also you have some crystallized materials, right? So this is one situation. Or otherwise, uh, you can have partial melting. That means you have a solid or the residue, and you can have the melt produced. So you have two phases. You have melt, residue. That means solid. Two phases, and here also the same. You have the crystals as well as the melt. Two phases. So anyway, what you are having here is solid and a liquid, and here also you have the solid and a liquid. So when this type of a situation is there, so these heavy rare earth elements usually prefer to partition into the solid phase. Okay, they prefer to the to partition into the solid phase because their incompatibility is less. Their incompatibility is less. That means their compatibility is high, right? So if you have a phase like garnet, for example, right? Because garnet is a very good host for many elements. Okay, so especially for heavy earth elements, garnet has a special preference. So if you have garnet, for example, in this case, if you have fractionated garnet from the magma as a fractional crystallization, right? So within the magma, you can have garnet formed, right? If you have garnet there, or otherwise, if you have uh, garnet in the solid phase, for example, in this mantle residue, you might have garnet. For example, you can remember the mantle rock called garnet leusolite. Okay, so we told that the mantle composition is leusolite composition. Remember, olivine, orthopyroxene, CPX. But you can have plus aluminous phases in addition to those main three phases. You might have spinel, garnet, or plagioclase, right? You have to remember that these mantle rocks can have the basic three foundation minerals, that is olivine, OPX, and CPX, that defines you the leusolite composition. Plus, you can have an aluminous phase. These aluminous phase can be either garnet, spinel, or plagioclase. Okay, it depends on the depth. The depth, that means the pressure, okay, within the mantle. If it is very deep, then you will have garnet. If it is moderate, you can have spinel. If it is shallow, you can have plagioclase. So in that case, you can have three types of mantle rocks. That means plagioclase lasolites, spinel lasolites, or garnet lasolites. Okay. So if you have garnet in the solid phase, for example, here, if you have garnet here, or if you have garnet here as a crystallized product, heavy rare earth elements from this melt, from this magma, will preferentially partition into this garnet phase because garnet is a very good host. So if you have clinopyroxene and garnet both together, right, a lot of heavy rare earth elements will go into garnet, and only a less amount will go into CPX because garnet has much accommodation for heavy rare earth elements. It depends on the crystal structure, valency, and many other factors. Anyway, garnet will accommodate a lot of heavy rare earth elements in this type of equilibrium system, right? Always remember this should be an equilibrium system also, because there shouldn't be any reactions, because if there are reactions, then this partitioning will be disturbed, right? Of course, the partitioning will be taking place, but due to reaction, there can be a lot of complications. So in an equilibrium system, heavy earth elements are easily partitioned into garnet-like phases. Okay, CPX will also take some, but garnet will have much higher preference. That means if you want to calculate the partition coefficient between the liquid and the solid, right, garnet will show the highest partition coefficient for heavy rare earth elements, right? So in this table, you can see that this is garnet. Okay, so this is garnet, and what happens for the partition coefficient if you consider the heavy rare earth elements? You take the heavy rare earth elements there, right? For example, these are the heavy rare earth elements that we considered before, the most heaviest ones. And you see the partition coefficient, right? Very high values, 3, 6, 11, like that. Okay, so that means they have the highest preference. So they have the highest preference to get into that phase, get into this garnet phase. Okay, right. So if you consider the light rare earth elements, for example, these ones, okay, if you take these light rare earth elements and okay, from here, lanthanum, right? So you see the light rare earth elements, they have a very low values, right? See, even for lanthanum, cerium, the highest incompatible ones, they have one fraction of 1,000, right? It's a third decimal point. It's very low value, right? You can also see some change when you go from lanthanum to say europium. You will see it is slightly increasing, right? That's why is that? Because the incompatibility also decreases from left to right, remember, from left to right. So that means they have some little increasing preference to the compatible side. That's why the partition coefficient little by little increasing. Okay, so this is the behavior or the feature that we showed here is clearly reflected. Okay, this feature we showed you is clearly reflected from the numbers also here. Okay, from left to right, right, from lanthanum to lutetium, that is increasing. Okay, so whenever you see some value greater than 1 for the partition coefficient, for example here, the chromium, it has greater than 1. So it definitely shows you the composition or the concentration in the solid phase, CS here, should be high to get a high value, right? To get a value greater than 1, the concentration in a solid should be greater than that in the liquid, right? When you compare. That's why you are getting values higher than 1. So if you are getting a value higher than 1 means it is definitely a compatible element. Okay, so but always remember these are very relative. Okay, they are very relative. So if you want to compare, for example, these are highly compatible two elements. Here you have the say ytterbium and lutetium here. Ytterbium and lutetium, if you consider their compatibility, their relative compatibility is high in lutetium compared to ytterbium. So that means ytterbium has a lower partition coefficient compared to that of lutetium. Okay, so that's why I told you that it's relative. So if someone asks, are these? Can you label the incompatible element between ytterbium and lutetium? If someone asks like that, a question like that, right? Maybe a kind of a stupid question, but still the question is valid. Okay, if someone asks what is the incompatible element between these two, if you consider these two elements, ytterbium and lutetium, then you have to say ytterbium is the incompatible element out of these two, right? But actually it is compatible, but in this particular situation, we are just considering only two elements there. So whatever the less compatible element, you can say it is relatively incompatible, right? Just comparing these two only, right? Otherwise, normally these are compatible elements, right? That's why I told you, just to understand the relativeness there. Okay, and you can see clinopyroxene also. Clinopyroxene here, you will see some partition coefficients are increasing downwards, but due to some reason, this lutetium doesn't show a higher value. I don't know exactly why that has happened there. I can't explain it, but maybe some effect in the crystal, or otherwise there can be some partitioning effect, or even it can be some experimental artifact, right? Without information, we can't say much on that. But you can see gradually the partition coefficients are increasing this way for clinopyroxene. Okay, even if you consider from middle earth element, from there onwards, it's increasing, right? And if you take the opposite side, you can see it has less compatibility. That means low partition coefficients towards the incompatible side. Okay, but you will see very clear, very specific feature here. You see a very big partition coefficient is assigned to chromium, right? This is chromium. Chromium in clinopyroxene, very high partition coefficient is given there, even greater than that of garnet, right? Garnet is 1 point something. So why is that? Due to the equal, chromium, the ionic size is almost similar to the calcium component in clinopyroxene, right? Clinopyroxene, you have a lot of calcium, right? Calcium is 2 plus, chromium is 3 plus, but the size of the two ions are almost similar. So therefore, chromium has a special place in CPX. So it can easily get into clinopyroxene. Therefore, there is a big partition coefficient for chromium, right? Even nickel has a high value, right? Due to the same reason. But the chromium is the more matching atom or matching ion for clinopyroxene. Okay. You'll see for orthopyroxene also, because these two both belong to inosilicates, right? OPX and CPX. So that's why they have higher preference there. So you can see the orthopyroxene. If you take the orthopyroxene partition coefficients just for comparison, right? So you take the orthopyroxene partition coefficients and see what are the values. Heavy earth elements somewhere here increasing, and you can see clearly increasing downwards. That means from left to side, compatibility increases. That means the partitioning should be relatively changing little by little, similar to this CPX and garnet, right? We explained before. But can you compare the values or the numbers? I mean, slightly okay for heavy earth elements because of point 0.1, point 0.2, point 0.3, like that. Even for CPX, you have point 0.5, point 0.5, something like that, right? But you see, uh, the light trap elements 0, 3, like, right? Even for neodymium, right? 0, 3. But for CPX, at least you had point 0.2, okay? And even CPX you had 0.9, means something like zero point 0.1, right? Even this one you can approximate to zero point 0.1, right? That means little higher, right? Relatively. But here it's 0.3. It's almost zero, right? If you just round off, it's almost zero. That means OPX has a very limited capacity for light rare elements. So these are the light rare elements. So for OPX, you have a very limited capacity for light rare elements, but heavy rare elements also you have a limited capacity for OPX. But since a little bit higher values are there, I mean, relatively, there is possibility for accommodation of heavy earth elements, but not like CPX or garnet. Okay, so if you consider these three minerals, OPX, CPX, and garnet, in an igneous system and measure their rare elements using you can use a ICP-MS, right? ICP-MS you can use and measure the rare elements, and if you see the concentrations, definitely you will see OPX is having a low value, okay, low ppm value, right, compared to CPX and garnet. CPX and garnet will have high ppm values of heavy rare elements. And light earth elements also the same. It does not accompany much into its structure, right? But you can see some nickel and chromium can be going there because there is a significantly high value, 5 and 10. Okay, uh, these two elements can be accommodated there, but the others are little, right? But for other minerals also you have very little values like 0.4, 0.3. So 0.2 is not that different, it's almost same. But anyway, for these elements like alkaline elements, these are alkaline elements, right? Rubidium, strontium, barium, remember, alkaline elements. Large and lithophile elements, same, we call them, right? So they have limited capacity in this OPX, CPX, garnet like uh, phases. But for phases like plagioclase, for example, plagioclase or even amphibole, okay, even amphibole, you can see some higher values, okay, for these alkaline elements. At even point 0.2 is not down, I mean, not bad, okay. It's not 0 point something, 0.0 something, right? It's not like that. So you can have an acceptable value. But for nickel and chromium, you see very low values, 0.1. So that means in plagioclase, you don't see much nickel and chromium, almost nothing. Okay? But you will see strontium, barium in higher amounts because you have a relatively higher partition coefficient. Even this one, you can round it off to 0.1, right? So that means it can accommodate some, right? Even amphibole, not bad. They can accommodate them. Right? For amphibole, you have nickel and chromium, high values. It's possible, right? And for magnetite, see, it's 29. What is that? Nickel and chromium 7. And light rare elements, see, it's very high. Light rare elements, so 2. That means a lot of light rare elements can go into magnetite also, right? Uh, in heavy earth elements also they can accommodate 1, 1, 1.5, like high values are there. So this is very characteristic for these minerals. And if you compare this one with the other important mineral, that is olivine, okay, so can you imagine how olivine can take these elements, right? Let's consider first the rare elements. light rare elements. You see how is the capacity? 0.007, 006, 006, 007, something like that. Right? Middle to heavy earth elements, 007, 01, 02, 04, 04 again, right? It's not that high, right? Relative to these other minerals. So that means olivine cannot take much of rare earth elements, right? Not only rare earth elements, alkaline elements also. Low, low, low. Okay, right? It cannot accommodate much. But see, for nickel is very, very compatible in olivine. That means a lot of nickel can uh, go into olivine. So if you compare with all these silicate minerals, right, up to plagioclase, sorry, up to amphibole, you can see the highest nickel taker is olivine. This is 14, partition coefficient is 14, right? So it's very high, right? Magnetite is not a silicate, okay? It's an oxide. It's not a silicate. So if you consider the silicate minerals, the highest nickel intake uh, is shown by olivine, right? So that's why you see a lot of nickel in serpentinite soils, right? In Ussangoda, if you go to Ussangoda, you see this reddish soil, iron and nickel. Iron is also there. A lot of iron is also there. Nickel is also there. The reason is Ussangoda is composed of periodic weathering soil, right? The dunite, the periodite, olivine-rich rock has now weathered. So a lot of nickel has released from olivine weathering. Okay, so that's why you have a lot of nickel in those soil. Okay, so this is how the partition coefficients are important in igneous processes. You can have different values, and in this case, they have in this table shows both basaltic and andesitic rocks. So that means both of these rocks have more or less similar partition coefficients. That's why they are uh, uh, combinedly shown in a one table, right? Maybe if you take another melt like granitic composition, these values will be different, right? But basic principle behind this compatibility and incompatibility will be there uh, irrespective of the real composition of the melt. But as long as it is a melt, then the compatible elements will be uh, loosely participants into them, whereas incompatibles will be going much into the melt there. Okay, right. So do you have any questions until now? Any questions? Is it clear what I am telling now? I mean, technically, do you hear well? And the screen is clear, or if something is lagging on the screen, do you feel anything? I can't hear you. Respond to the mic, please. No, mic not working. No, you check the switch and why are you so slow? Respond quickly. අර 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 අත්තල කිරියම්මල ටිකක් වගේ. අඩු ගානේ හූ කියලාවත් කියන්න මොකක් හරි. බැරිම නම්. ඇහෙනවද මං කියන්නේ? ස්ක්‍රීන් එක ඩිලේද මොනවා හරි තියෙනවද ඩිලේ එකක්? ඈ? මොකක් හරි කොඳුරනවා වගේ ඇහුණා. ඔය මයික් එකට පොඩ්ඩක් තට්ටු කරන්න.
We can hear you.
Okay. Now I can hear you too. Okay, right. I can see a message. Okay. But I need to know whether mic is working or not. Yeah. Okay. Anyway. Okay, right. So if you have no questions, let's move further. Okay, right. Now, a very important thing. This is about rare earth element diagrams, right? So these are very frequently we use uh, in a lot of petrological and geochemical interpretations. So therefore, you need to know how to interpret these rare earth element diagrams. So these diagrams are made with these rare earth elements ordering. So you see here, it is ordered in the same way as you see in the periodic table. Okay, from left to right towards, in the way of increasing atomic number, right, from lanthanum to lutetium, right? So remember, in this series, we do not take this PM, promethium. Okay, it's not natural. Therefore, we don't take it there in the rare earth element interpretations. Okay. Okay, and therefore there's another thing, right? When you draw these rare earth element diagrams, right, you order it. So at the place when you put neodymium, okay, when you put neodymium and then samarium comes there, but because this is missing, we are not taking this promethium PM in the diagram. In some diagrams you will see there is uh, a space here. I mean, you don't straight away put samarium just after neodymium. You just keep blank there and then samarium at the next place, right? So that way is more appropriate. Uh, but just for showing here, you can see everything is together one by one. Okay, but you will see that difference in some, not some, most of the rare earth element diagrams. Okay, so the basic idea here is we plot the concentration, right? We plot the concentration against these rare earth elements. That means each and every rare earth element concentration in ppm, you can put there in the y-axis. Okay, so increase in atomic number is important, and you can see the degree of compatibility increases from left to right, as I mentioned, right? Compatibility increases, right? That means incompatibility decreases. Yeah, sometimes this is called lanthanide contraction, right? But it's not very important for us. But you might see this one in the literature in some cases. But in geology, we don't hear it much. Maybe in chemistry, you may hear it. Okay, right. So the concentration is put on the y-axis. So this is what you call the rare earth element diagram. Some other term was there in previous literatures, but nowadays we just use RE diagram, the term RE diagram, right? Previously people used this as what do you call, I forgot it. Sorry, I will remind it later, right? I forgot it because we don't use it much now. Anyway, just keep in mind RE diagrams, okay? Right. So this is it again. You can see we omit this one, and also you can see here we don't have some in some cases in some diagrams you might have this one, this H, not H, H, yeah, HO is also missing. We don't take much because we can't analyze it in ICP-MS or whatever the techniques. We don't see clear, clear. I mean, there are what do you call? There are interferences. Okay, interferences are there, so you don't get the correct concentrations for that. That is also not possible to make. Uh, then, due to some reason, some people swap these two, right? It's all depends on some interpretations, right? You can have these two just following the atomic number or just following the incompatibility or compatibility thing. Some people prefer to follow this in terms of the compatibility. So in that case, so this er might come before uh, dy, right? Here you see er is before dy, right? Such very minor things are there, but you don't much get into that into your attention now at this stage. You don't need to bother much on that. But anyway, it doesn't matter. You can take any order there. Okay, and these are also ignored. We take YB lutetium here. Okay, right. So after dy, you can have HO, or you can sorry, you can omit HO and you can have ER, or otherwise you can change the order, but it doesn't make big trouble. Okay, so these two anyway comes in this order, right? So up to here, no difference. Up to here, no difference, but you can simply follow this order. This is okay. Okay, this is okay in many igneous, not only igneous, metamorphic or whatever the geochemical studies, you will see this type of ordering, right? But definitely, you can consider the degree of compatibility increases. In that way, you can order these elements, right? So if you put these elements, right, in the y-axis concentration and x-axis atomic number, right? Of course, here also the atomic number, right? We are increasing the atomic number, although there is confusion here. Don't think much on that. We can put the atomic number instead of these elements, names, okay, symbols. So this diagram is something like that, right? So the atomic number is given from 1 to 100, right? All the naturally occurring elements are there, covered there. And if you put the composition of these elements or the abundance composition in chondrite meteorites, chondritic meteorites, okay, the chondritic meteorites means the building blocks of the earth, right? Planets, right? Building blocks. You remember the primitive mantle. The primitive mantle was fractionated or differentiated from chondritic materials, chondritic meteorites. So that's why we consider them as the building blocks of the planets. Okay, so originally we should have this type of a concentration in these elements in meteorites, chondritic meteorites, right? So this is given as log values because their variation is very high, very large variation. Some are very low concentration, some are very high concentration. So therefore, if you put just 1, 2, 3, 4 scale, that will end up in thousands up there, right? So you can't make a comfortable graph there. So therefore, it has been put in a log scale with log values, okay, logarithmic values, so that you can shorten the y-axis. That's the only purpose there. So how do you think this variation, is it smooth or kind of disturbing pattern? If this pattern was observed like that, right, it may be a very smooth pattern, right? We can say it's a smooth pattern. But now I mean one by one, right? here one element and the next element and next element here, next element here, next element here. If you had something like that, it's sort of smooth. But here it's not smooth, right? So you will see some values are very high, some values are very low, some values are like that. So it's like a very disturbing pattern like that. Okay, so it's not smooth pattern, it's a very different pattern. uh, it's far away from a smooth pattern. Okay, so therefore we call this effect, this is a kind of an effect actually. If you, these are the real values, they are actual values of concentrations. So once you plot them, you definitely get this type of disturbing pattern, right? This zigzag pattern. Okay, we call it zigzag pattern also. So this is called Odo-Hawkins effect. Okay, Odo-Hawkins effect. This is named as Odo-Hawkins effect. Right. So we have to eliminate this effect to make Y scale more comfortable for us. Okay. So therefore, what we do is we use a normalizing value that can be considered as a standard, right? So that means each and every concentration of these values will be divided by a, uh, uh, a standard material, right? For everything to be more fair, right? For everything to be more fair, the primordial mantle composition is taken. Okay, the primitive mantle composition, right? So the earliest mantle composition, the primitive mantle composition. This is now present day. If you can dig into the Earth's interior and pass the mantle, upper mantle, and then lower mantle. If you reach the lower mantle, the lower mantle will reflect more or less similar to this primitive mantle composition. I think you can remember we mentioned this sometime at the very beginning, right? The lowest part of the mantle is still undifferentiated. Like we assume that, right? That's why these some clues originated from the melts coming from very deep part of the mantle, low mantle, like plume type of magmas, right? They bring up lower mantle materials which are very close to the primitive mantle composition, right? The melts you find in mid-ocean ridge or in a volcanic eruptions like there, they are very different because they are coming from upper mantle melting. So upper mantle is heavily differentiated. That's why the continental crust is formed from upper mantle, but lower mantle still remains close to bulk silicate earth. Okay, close to bulk silicate earth. That means the primordial mantle composition. So therefore, anyway, as a to make it a standard, it's better to have a more kind of unbiased unbiased material which is not affected much. So therefore the lower mantle composition, which is similar to the primitive mantle, can be considered. Okay, so this primitive mantle composition has been determined. Now there are some publications. I will give you I mean the most appropriate publication, which is cited heavily by now, because everybody considers that is the real composition, okay, of the primitive mantle, right? It's from McDonald and Son, 1995. Okay, so later we will see that publication. So anyway, that composition is taken uh, in some estimates, or otherwise people another option is to use the real chondrite composition, this real composition, these values, to normalize whatever the sample that you are going to plot, right? Right, so chondrite composition itself to use, because that is the real building block of the planets. So original composition, that means even before to make the bulk silicate earth, because co-separated first from these primordial compositions, early compositions, co-separated, iron and nickel separated out, remaining the leaving out the silicate portion. That is what we call the bulk silicate earth, right, or the primordial primitive mantle composition. But even before that differentiation, we can take the original chondrite meteoritic composition, which is prevailing. Even now, if you happen to find a meteorite, some meteorites are chondritic meteoritic composition. They are unfractionated. If you are lucky to find a very unfractionated one to collect somewhere pollen, right? But you know these chondrites, these chondritic meteorites. Actually, these are chondrites, right? They become meteorite once they hit our atmosphere, right? Atmosphere and then get burned, right? Then comes as a burned material. In the night sky, you see these meteorites, but before getting them burned, those are chondrites. Okay, but there are chondrites found. That's why people use them to find out the Earth's age also. Uh, that composition also used as a standard. Okay, so remember, for rare elements, mainly we use this composition uh, than even the primordial mantle composition. But for some situations, we use this primordial mantle composition also. If you want to consider all these elements, right? If you just pay attention to the rare elements, then we use this chondritic meteorite composition. Okay, because this shows unchanged composition or unmodified composition of primordial material, so that is the most suitable standard. But if you take the rare elements, other everything together from alkaline earth, high field strength elements, and everything, if you want to plot, right? Normally, what we do is we take this primitive mantle composition. Okay, so remember, for earth elements, we prefer to use chondritic composition, but for all earth elements, if you want to use, people use this primitive mantle composition. So that is two applications in igneous and metamorphic, or whatever the geochemical interpretation. It's a matter of choosing of the standard, right? But remember, more than 90% people prefer to use chondritic mantle composition, chondritic meteorite composition as a standard for rare earth elements. Okay, right. So we'll see some of these ones in some diagrams later. Okay, right. Okay, now I want to ask you this question. So we plot the rare earth elements. So definitely we take the chondrite composition, because I said it is the most preferred standard used for rare earth elements. But if you wanted to use all the trace elements, other elements, including high field strength elements, alkaline, whatever, everything, right? Then we go for primitive mantle composition. Okay, PM, primitive mantle composition, right? But in this case, our sample, our whatever the rock that you are analyzing should be normalized. Otherwise, your rare earth element pattern will be very zigzag type, right? I mean, it's not only for meteorite, whatever, for the sample, you will have this type of disturbing pattern. That is what you call the Odo-Hawkins effect. To eliminate that Odo-Hawkins effect, we have to normalize it into a standard. So now we have chosen a standard as the chondrite composition. The chondrite composition is here, right? This is the chondrite composition. Although chondrite composition itself is disturbing, right? If you plot it as it is, but you can, I mean, as a standard, you can use that composition for your samples to normalize. Right. Now, suppose you take these compositions, this chondrite composition, to plot in this diagram after normalization. So you use your chondrite composition uh, to plot in this diagram, but your standard is also, that means your normalizing standard is also chondrite composition. So what would be the pattern you are getting? Because we want to eliminate this pattern, we want to eliminate this pattern, because if you don't normalize and plot, you will get this type of a pattern. Okay, what you want to do is you normalize it and make it a very smooth pattern like that. Okay, but now your sample is also chondrite, your standard is also chondrite. So what will be the shape of this pattern? Can anybody tell me what would be the pattern and from where you can draw it? Right. Okay, I put it a scale here: 0, 1, 2, 3, 4, something like that. Okay, you have the same scale here. You have the same scale here anyway, right? So what would be the pattern if you normalize it? Maybe like this, steep slope like that, or something like this, or uh, again maybe like this pattern. What do you expect? What kind of a pattern? I mean, it will be smoothened pattern, but it can have different shapes also depending on this trace element pattern, because you remember their compatibility, incompatibility matters, whatever it is. But anyway, now we are taking not just a mineral or anything. We take the entire sample, chondrite, and now we use the chondrite itself as the standard. And what would be the pattern? I mean, it's easily explainable, so that's why I am asking. You don't have to draw or anything. You should be able to tell that pattern how it would be. What would be the pattern? Tell me, someone. Okay, we'll start from the first row. If you can imagine the pattern, just tell me. Sorry. Can you tell me? Just a minute. Yes. Anybody? Just tell me. Take the mic and tell me what is the pattern you expect. Nobody can. It's okay. You can make mistake. Just tell me. We don't have much time. What would be the pattern? I want you to talk. No one is brave to tell. Yes. Okay. You just type and let me know in the chat. Tell me. Okay. I will give you like some example. For example, you can say an concave shape or convex shape or something like that. You can just tell me what would be the pattern. Or you can have say how, yeah, straight line, or circle, or I mean this type of a curve upward. Oh, light earth element enriched curve like that. Oh, heavy earth element enriched curve like that. What can be? Concave. I have received an answer saying concave. Okay, one answer. Anybody else? What about others' opinions? Everyone agrees with that. Oh, some others have some other answers. Yeah, you discuss and tell me if others say another answer, because I'm not sure. I mean, I'm not telling that this is correct or wrong now. It's better to have two answers. At least one will be there with another opinion. Yes, quickly, quickly. Someone will type it. Tell others. Or you can speak. Yes, great. Sorry, I don't hear you. What has happened? Something wrong with the mic, maybe. Because I heard when Danushka speaking very well, so my settings are okay. Something to do with your mic, I think. Upward slope. That means how? Like this? No, no, that is downward. Eh? Like this? Concentration increase from light earth elements to heavy earth elements. Like how? Like this? Oh, like this? I don't know whether you can draw in the board. Is it interactive? You just try, please. I think no special permission is required, right? For Zoom, you should have this marker, the pen, the in the smart board. Let me check. No, I don't think. Why this mic cannot be used? Okay. You. Okay. You expect like that? Okay. We have two answers. Oh my God. What is the question? Anyway, it's good for අර නිදිමත යන්න නියමයි වැඩේ. Okay. Okay. See, what is the question? What would be what is it? What would a rare earth element diagram look for an analysis of a chondrite meteorite? Okay, you understood the question very well, right? Okay, so we'll go back. So this is a concentration of a chondrite meteorite. So you don't, I mean, we are taking the standard also, chondrite meteorite. Okay, right. So your sample is, because in this case, so what we do is, we take sample and it divided by chondrite composition, as we need to standardize it, and then we try to plot it. Okay, right, that is what is expected. Otherwise your sample concentration will be something like very zigzag type, right? Just to avoid that, we are doing this to just to make it like this or like that, or as you said, like this or whatever, anyway, straight line or whatever, and just to make it smooth pattern. Now that is done by sample to chondrite. This is how. Okay, right. Now what is your sample? You have a chondrite meteorite, your sample. What is your standard? Again, chondrite meteorite. Okay, so you analyze one chondrite and you have a the standard is also chondrite. Don't you think these two are equal? At least almost equal, given that these two chondrite samples are taken from two different locations. But still it is chondrite, isn't it? It's primordial composition. So then, say you have lanthanum in your sample, right? Sample is also chondrite. Now we are considering, I mean, our sample is chondrite. So say it had lanthanum in 2 ppm, right? What is your standard? Again, chondrite. Okay, maybe say just you have very little difference, 2.1 or something, or even 2, which can be approximated. So then what would be the final answer? Your normalization is just simple division. Okay, normalization, 2 divided by 2, it's 1. Okay, so what about samarium? Your concentration, maybe you had 8 ppm of samarium in your chondrite, and your standard also should have very close to 8, isn't it? Because that is the same material. So then your normalization value should be 1 for samarium, right? Even if you do the same for lutetium, maybe you had say 28 ppm lutetium in the chondrite, your standard will also have 28, right? Very close to that value. So approximately you are getting again 1, right? So this is 1. Okay, this is 1. Your lanthanum was 1. Your samarium was 1. Your lutetium was 1. So likewise, everything will be 1. So then what would be the pattern? Your pattern will be something like this. It will be a straight line almost. Okay, so why did you want to say it is like this, or increased increasing concentration or something. Why did you want to say like that? Because we did not talk anything about fractionation here, right? So if you had any fractionation effect, right, maybe heavy rare earth elements would be more like to go into the solid phase. So therefore, you can think of going it up. Okay, but there was nothing, no fractionation. We were talking about just chondrite meteorite. We have some concentration and we normalize it to the chondrite. Again, chondrite divided by chondrite. Okay, so for a chondrite meteorite, if you plot the normalized concentration, it will be just a straight line. Okay, just because it is just one, it's equal composition, right? If you had your sample concentration double the chondrite value, right, double the chondrite value, then you will have definitely some value here too. If these are also increased like that, so in that case you may see some change in the pattern, right? But here we did not talk about any fractionation, just we considered a sample of a meteorite, and it was standardized into the chondrite composition. Okay, right. So just keep in mind what you have to see is you need to focus on what is your standard and what is your sample. Okay, so that is very important. So if you take the primitive mantle as the normalizing factor or the normalizing parameter, then your shape will be different. It won't be a straight line, right? Because your primitive mantle will have different composition than your chondrite material. So therefore, because the elements are fractionated in different ways, so therefore you may have a different pattern, but still it will be, I mean, it won't be one, but still it will be uh, uh, like close to a straight line, because the changes will be very minimal. Okay, I mean, co-fractionation only happening in the primitive mantle, right? Co was fractionated. I mean, you had the meteorite here, chondritic meteorite composition, and then what happened? Our Earth was formed, and Earth formed, and first what was forming there? The core. Okay, but for this core, you had a lot of nickel and iron gone there, but all the other elements are still lying here. So that's why we call it bulk silicate earth or the primitive mantle, right? So very slight change might have happened during this fractionation, because during this, sorry, not fractionation, differentiation, because some volatile elements like lead, uh, especially lead, like some volatile elements may have gone away from the system. So that makes this primitive mantle little different from the chondrite composition. Okay, likewise, some elements may have lost. Even actually, this lead still we can't trace where it was lost. Now, the present day, or the I mean current, the bulk Earth doesn't have the same lead budget as it was supposed to. Similar, I mean, when you compare it with the chondrite composition, right? So there are a lot of arguments where this lead has gone. That is what you call the lead paradox. There is something called lead paradox for that, right? So likewise, there are some other elements, but not all, may have adjusted slightly compared to the chondrite composition. So therefore, you may have a slight variation, but I mean, the this straight line behavior may have slightly changed, but not that much, right? I mean, not like this or like this or like that. I mean, no drastic change could be expected. Okay, right. Okay, it's good anyway. Yeah, you got interacted, and it's very well. I mean, it's good for you. Okay, right. Now, let's move a little bit more, uh, and we'll consider the rare element composition or the diagram for a batch melting model. Right. I think we considered this for just for one element in the previous slides. You can remember. we made similar type of uh, curves, right? Many curves we've made like that, right? Considering different fractionations, different amount of degree of melting, or yeah, something like that. Remember in the last week? Okay. So different values, various values of F. What is F? Degree of melting, right? Batch melting, degree of melting. So you have original material, you make a melt out of that, maybe 1% of melting, and then 2%, 5%, like that, right? You can have different degrees of melting. So the higher the melt produced, you will have higher the trace elements going into that. But you remember, for the first uh, fraction of melts generated in batch melting, it could take up a large amount of incompatible elements. Remember, we considered two cases for heavily incompatible element and heavily compatible element. You remember, we had graphs like that, and another one like that last week, right? So that means at a very little degree of melting, a large amount of incompatible elements will be going there. Okay, so that means the first melt to form, right? Uh, Very little amount of melt. If you produce, there will be large amount of incompatible elements like these will be accommodated into that melt. So that's why this the first produced melt will have the highest composition. Okay, only difference is your concentration is divided here with the chondrite composition, right? Just to smoothen the pattern. Otherwise, here also you will see very I mean very uncomfortable pattern, or very zigzag type pattern with this Edo Hawkins effect. And you increase the melting, and a lot of incompatible elements have already gone into the previous melt. Therefore, the remaining incompatibles are a little low. Therefore, you are having little low compositions compared to the previous melt composition. Okay. So likewise, you will see your melt composition decreases in terms of incompatible elements. But the compatible elements don't show very big difference, because compatibles are normally not accommodated into the melt, because here we are talking about the melt. We have the concentration of the melt here, so you can see the caption also. It says the melts produced, right? We are measuring the melt now here, right? So for the melt, the compatibles are not going much. Therefore, even though it is uh, first melt or little melt or whatever, you don't see very big variation. Of course, there is a variation, but not very big variation. Okay, because they are mostly remaining within the residue, right? Here you have residue, so a lot of compatibles are left here in the residue, and a lot of incompatibles are going into the melt produced. Okay, so gradually, if you increase this melting, you will see uh, the concentration will get down and down, and finally, almost it will be equal, right? Because there will be a certain point, because you can't go up to 100%. This is very difficult. This is not possible. Actually, it's not feasible, because you need a lot of energy for doing this. Uh, but at a certain position you have to stop this melting. I mean, the melting will stop naturally, right? Even though you however much you put the heat, it won't melt further, right? So then we call that as the heavily refractive residue. Heavily refractive residue, this is a term we use. Heavily refractive residue means you cannot produce further melt out of that residue. Okay, you cannot produce further melt, you cannot accommodate any further melting, even though you try to heat it much and much more, right? So that means its capacity, heat capacity is very, very, very high. You need enormous amount of heat to melt that highly refractive residues under normal circumstances prevailing within the mantle region. You can't melt it. Of course, if you can put some extra heat somehow, right, artificially, you might be able to melt it. But otherwise, you can't do that. I mean, we are talking about the natural process here. Okay, we are talking about the natural process. So naturally, you can't melt beyond a certain point. So that point is the refractive, the highest refractiveness of that particular residue. Okay, right. So this is how you get the composition of the igneous melt, which is formed after melting, right? So we have here the rare earth elements, and you have to note that the heavily incompatible ones are showing higher values relative to their compatible counterparts. Okay, relative to their compatible counterparts. This is happening. So if you measure the composition of the residue, you will observe a different thing, right? Opposite thing. So there you will see some variation like this, right? You are supposed to see a variation like that in the residue, because in the residue, the more you remove the melt, the more you concentrate the compatibles. Okay, it's like just a removal of incompatibles from the source means it's automatically enriching the compatibles, right? It's like here you have the classroom. If 10 boys and 12 girls are there, so you ask 5 boys to go away, then what happens? The concentration of the girls will increase. No girl came in, right? But the system itself adjusted its composition accordingly, right? So similar thing will happen there. Okay, so it will naturally get increase the composition. That's why you will see this type of behavior. Just to smoothen it, we make it normalized with the chondrite composition, right? So you have chondrite compositions given in standard references, and that composition you can use for your sample normalization. You can do this in a normal Excel sheet and easily plot this one. It's not difficult. Okay. Anything not clear? Do you have anything to clarify? So here it is said a garnet leusolite. It doesn't matter, whatever. Okay. If it is garnet leusolite, it's very hard to melt, because whenever you have a phase like garnet as an aluminous phase, the amount of heat required to produce partial melts is very high, getting more and more higher compared to mantle source which contains spinel or plagioclase. Right? You remember I talked about the mantle composition. The three foundation minerals are olivine, OPX, and CPX, right? Olivine, OPX, and CPX. In addition, you have what? Garnet and garnet, spinel, and plagioclase, depending on the depth. Okay, the higher the depth, that means more deeper, you have garnet. Intermediate, we have spinel, right? So that means the deeper you go, the harder the effort you need to make it produce. I mean, the melt produced out of it, right? In shallow conditions, it's not very difficult to do melting. So that's why a lot of shallow mantle, like mid-ocean ridges, produce enormous amount of melts. Heavy amount of melt, the basaltic melt is produced because of that. It is shallow. When it is shallow, less heat is required. So convection itself is very sufficient for these igneous materials to be produced. Okay, so this is the difference. Okay, right. Okay. Yeah. I forgot one thing to mention here. Since this is a garnet laserite, okay, means you have garnet in the source, in the residue. Okay, you have garnet in the residue. So having garnet in the residue means here, for example, you have some garnet, right? Some model percentage of garnet is there. We talked about partition coefficients of garnet previously. Remember garnet here? You have the partition coefficients of garnet. So what did we talk about there? The heavy earth elements. Partition coefficients of garnet is very high, right? Relatively high. So that means they prefer very much these heavy earth elements compared to light earth elements. Okay, so see the behavior here. The heavy earth elements are here, and you can see relative to the light earth elements, the concentration of heavy earth elements in the melt is low. Why? Because you have the garnet there in the residue. A lot of heavy earth elements prefer to remain in the residue rather than get accommodated into the melt because their compatibility is very high. Okay, especially when garnet is there, a lot of heavy earth elements will remain there in the residue. All right, so this is a very characteristic feature. So that means in your residue, if you measure, you will see like this very high concentration of heavy earth elements. Even like these patterns, you may observe very high numbers, very high values of concentrations. So these things we will discuss separately by looking at trace element patterns or rare element patterns. We can infer whether garnet was there in the source or not. Okay, we can easily we can easily understand that in the residue whether garnet was there or not. If garnet was not there, for example, in this situation, you might change this pattern. For example, if you had the cyanopyroxene or spinel there much uh, and no garnet, your composition might be something varying like that, little above, not like I mean, not as low as this level, right? At least there or like this, maybe changing because the garnet is a sink for this heavy earth element. It attracts everything, heavy earth elements, as much as possible. That's why you get very much depleted heavy earth element composition in this melt, in this particular melt. Okay, so that will change. I mean, the phase which is available in the residue will determine the shape of your uh, pattern, right? Even the trace of the shape of the pattern of the melt or the residue, both is determined by the phases available in the original source, right, which was subjected to melting. Okay, now let's see. In some trace element patterns, you will see this type of a specific feature. Okay, so you have the pattern, a very smooth pattern, but suddenly you see some negative anomaly like this. Okay, maybe you have trace or earth element pattern like this. Okay, you have a pattern like that, but here it is exactly corresponding to European. Okay, so if you have European there, what would happen? So this is European here, and you see a depression there, right? So we call it a negative anomaly. This we call a negative anomaly of European, right? So this is caused by plagioclase, the presence of plagioclase in the residue. Okay, so the presence of plagioclase in the residue is given, I mean, reflected by this type of a large anomaly of Europe. Why we call it anomaly? Because the smooth pattern, normal pattern should be like this, very smooth, but all of a sudden it gives a strange value. Therefore, it's an anomaly. It can be in other way also, like this also. In that case, we call it positive anomaly. but in this case, this is a negative anomaly. Okay, right. So positive anomaly, negative anomaly, these can be present in rocks. But if it is related to europium, then there is a direct relationship with plagioclase. So plagioclase has a direct relationship with this type of anomaly with europium, right? So uh, it's not only in the melting phase, even in a magma, if it crystallizes some minerals, like suppose you can have different minerals crystallized during the ascent of magma. During the magma is coming up, a lot of materials get crystallized, right? This is what we call the fractional crystallization. We didn't talk much about the fractional crystallization, only we talked about much on the melting. The opposite of melting is the fractional crystallization. I mean, opposite of partial melting is fractional crystallization. Because why we call it fractional crystallization? Because the entire melt, sorry, the entire melt doesn't get crystallized, right? Only a fraction gets crystallized. So therefore, fractional melting, fractional crystallization, like the partial melting. The entire solid does not get melted. That's why we call it partial melting, right? So phenocryst, for example, in igneous rocks, you see this is happen. That is formed like that, fractional crystallization. So if this fractionating phase is plagioclase, right? If this fractionating phase is plagioclase, then a lot of europium will be going into this plagioclase. So therefore, the rest of the melt will be depleted in europium, so that it will reflect this type of europium negative anomaly if you plot its composition. Okay, so if you see a huge europium anomaly, negative anomaly in your rock, that indicates your rock has suffered some kind of plagioclase involvement there. Okay, so even during melting, if this happened, the residue, if plagioclase was there, a lot of europium will be leaving out in plagioclase, and rest of the rare earth elements will go away with the melt, so that your melt will be depleted in europium composition like this, right? Giving you a negative anomaly, right? The same thing can happen, right? So it can be a fractionating phenocryst or even residual solid where plagioclase is present, right? So this will show you this type of a negative anomaly. And so this europium negative anomaly is sometimes showed as europium star. We call it europium star value, right? We take the average of, there is a way of calculating this the magnitude of this europium anomaly. Because in some rocks, you may have very slight anomaly like that. Some rocks may be moderate. Some rocks may have a huge anomaly like that, right? You can calculate the degree of this anomaly, right? It's what you call the europium star value. If you put a value for that, it is the degree of europium anomaly, right? There is a way to calculate it, but I'm not going to tell you now how to do that, right? So anyway, uh, uh, in this case, the diagram says RE diagram for 10% of batch melting of a hypothetical leusolite, that means mantle composition, with 20% of plagioclase. So in the residue, uh, that means you had already 20% of plagioclase there. Okay, in the residue had 20% of plagioclase already there, and this produced a melt by partial melting, and this melt is reflected here. Okay, because of this plagioclase presence, a lot of europium would have accommodated there, so that your melt, when you measure it, will give you this type of a negative anomaly. Okay, with this anomaly, actually we call it with reference to the neighboring two elements, right? So you have the neighboring two elements. There should be neighboring two elements, close by elements. If you have measured these elements, that's okay. Otherwise, whatever the neighboring element you can consider, right? Normally, samarium, right? For example, in the previous case, uh, here samarium is not there, but still you can plot it so that you will get some negative anomaly if plagioclase is present. Anyway, don't think much on that, but just keep in mind negative anomaly is caused by presence of plagioclase. Okay, so this is a negative European anomaly. So this is a very characteristic feature of any magma which has fractionated plagioclase as a phenocryst, or a magma which has been uh, produced as a result of partial melting, where plagioclase was present in the source. Okay, so this is how we interpret this plagioclase, I mean, a European negative anomaly. So this is a very prominent anomaly. In many rocks you can find this, because in many rocks you have the plagioclase. Feldspar is very common mineral, so therefore most of the rocks will carry this type of anomalies, European anomalies. Okay, right. So I think this is what I have planned for today. Okay. I forgot. I just remind. I mean, I could remember that name. This is called spider diagrams, right? It was an old term, right? Do you remember? I told you. I forgot the term spider diagrams, right? But now, if we use the REs only, then we call it RE diagrams, not spider diagrams. But if you put everything there, uh, you can call it spider diagram, but still it's now becoming an obsolete term. But later we will discuss that later on. Okay. So far we considered only the rare earth elements. So therefore we considered only the rare earth element diagrams in this discussion. RE diagrams. Okay. Right. So do you have any questions on this content? This is very important because you need to see these anomalies, or the shapes of these patterns, so that you can interpret many things based on your geochemical data. Okay. Right. So if you don't have question, I will stop here for today. Don't forget the attendance.